So today we talk about new materials for space application. In aerospace engineering, damage tolerance design is used to develop complex structure. Damage are accepted, monitored, and repair program are applied. However, there is a large number of situations where repairing is not possible. If we think about space application, repair of a damaged component is linked to high risk, high cost, and sometimes even impossible. This became a challenge when the component that is damaged is protecting astronaut, like for example spacesuit during extravehicular activities. Spacesuits are the only barrier between the humans and the space environment. In this view, the development of new material with a new functionality can help to the answer of safety and create new material and new component for prolonged mission, prolonged Mars exploration and Moon exploration. But what are the threats that we found in space? We all know that space is an hostile environment for human activities. We found different threats. We have high vacuum. At this level of vacuum, our liquids, the liquids in our body boil. We have radiation, so UV radiation, IR, and cosmic ray that can create damage to our immune system and DNA. We have variation in temperature. So depending on the mission, we go to minus 100 degrees up to 100 degrees, also around the Earth, but also on the moon surface. We have the risk of impact with space debris that can cause damage, impacting at hypervelocity on structure and on astronaut during extravehicular activity. We have also, in case of moon exploration, dust. This kind of dust have a characteristic dimension of nanometers, and it is very dangerous for the health of the humans and the astronaut. For this reason, spacesuits were developed and invented, and I like to call them personal spacecraft, because they allow to the astronaut to make different operations in space, like a spacecraft. If we look inside, there are several components. We have garments for comfort and thermal equilibration. In particular, the garments for thermal equilibration have a complex system of pipes that exchange heat with the body of the astronaut. Then we have the so-called Snoopy cap. That is a cap that allows the communication with the spacecraft and the ground. And of course, all the system linked with the support the life of the astronaut that provide oxygen, in particular the PLSS, that is the backpack that the astronaut wear and provide oxygen during the operation outside the spacecraft. If you look outside, we have different components assembled together, starting from the upper torso, that is the rigid vest, where all the other components are connected by, for example, a metal attachment, and also we have straps for different devices during space exploration. We have the lower part or lower torso, the flexible legs and attached steel metal attachment. We have boots, maybe not very fashion, but very useful when you make the first step on the moon, for example. Then we have still a flexible section, the arms, and the gloves. Finally, we found the helmet that protects the head of the astronaut with all the accessories like light for dark condition. So a very large amount of components for our spacesuit. You have to think about that it will take about 40 minutes for an astronaut to wear the spacesuit before an extravehicular activity, so a prolonged time. What are the secrets about spacesuit? How they can protect astronauts for all the threats that we found in space? The answer is their multi-layer structure, where different layers made of different material solve different functions. If we start from the outermost layer, we have different fabric, polymeric fabric coated by Teflon for thermal protection. Then if we go more inside, we have still polymeric fabric, in this case coated by aluminum for radiation insulation. Then, if you go in the internal part, there is other polymeric fabric, Dacron and nylon in this case, that maintain the shape of the spacesuit. So during pressurization, you have to maintain the shape of this inflatable structure. And then, very important is the bladder. The bladder is a fabric, nylon fabric, coated by an elastomer, neoprene or urethane, that do not allow any flow of oxygen from the internal to the external part of the spacesuit. So maintain the atmosphere inside the spacesuit and allow the ozone to breathe. Of course, spacesuit can be damaged. Damage can happen in different situations, starting from the launching, the folding of spacesuit before the launch, but also during activities. So the higher risk came from puncture or from impact from space debris. You can see here in the video the astronaut that fall down on the moon surfaces, and the risk to impact with sharp rocks on the surface is a risk of damage. But also during operation around the spacecraft or around the International Space Station, where sharp edge of the spacecraft or sharp edge of the tools that the astronaut is using can damage the spacesuit. In both cases, there is the high risk of impact with debris. Why the risk of puncture is so high? Because it can lose pressure, can cause depressurization of the spacesuit, and the astronaut, depending on the damage, the extension of the damage, have a few minutes to come back inside the spacecraft safely. In particular, for an hull of 4 millimeters, the astronaut have only 30 minutes to come back inside. This time, you think that is enough on the ground, but in the space, without gravity, is not enough. Sometimes it will be very risky to come back inside in this situation. This kind of damage, of course, cannot be repaired in the space, and when a damage of this dimension happens in spacesuit have to bring back to the ground to repair. So, to have a possibility of repair on site, the idea is to insert a layer of material, self-healing material, able to repair itself without intervention by the astronaut. So an automatic repair of the spacesuit. But what is self-healing? Self-healing is the capability of a material to repair a damage, any kind of damage, from a mechanical damage or a chemical damage and so on. We can find this kind of feature in biological system. If you look about plants, if you make a scratch on them, there is an healing agent that came out to repair the damage. This is an example of self-healing system. So plants is a good example of self-healing system. We have other example of a self-healing system, for example, our body. So if you break one of your bones, it will take some time to repair. But also if you make a wound on your skin, the vessel, the microcapillars in our body provide the healing agent exactly in the zone of the damage, repairing it. So the question is how we can transfer this repairing system to a technical material or synthetic material. The idea is to copy what nature does. So we use a biomimetic approach. We have to create a material that is able to sense the damage, activate all the mechanism for the healing, provide the healing agent exactly in the region of the damage, and repairing it in a short time. In nature, this kind of mechanism can take also 1 year. For example, to completely repair your bone, it will take 1 year. So the synthetic system or synthetic self-healing system should follow all the mechanism for healing and have a quick response. Researchers started to use this biomimetic approach to develop different self-healing systems that are separated in non-autonomic or autonomic, depending if they need an external trigger to activate the healing. And another definition of self-healing is extrinsic or intrinsic, depending if the healing agent is added to the material or the material itself have all the ingredients for the healing. These kind of approaches are implemented actually to all classes of material, ranging from polymers to ceramic and metals. And for our application, polymers are the more promising, because give enough flexibility to design a self-healing system, and also have the right heating performance in the range of temperature that we want. So, focusing on self-healing polymers, we have the extrinsic one, where the heating agent is added to the material. So here the scheme of these approaches, where capsule or vascular are embedded in a polymeric matrix. When the crack propagates inside the matrix, broke the cracks, the healing agent flow out, reacting and repairing the damage. This one is the sketch, here the real material, so a composite with capsule inside, and here a composite with vascular inside. You can see when the crack propagates inside, the healing agent flowing in the damage, repairing it. This is for the extrinsic. If we go to intrinsic one, in this case it's the chemistry that plays the big role. There are reversible interaction, reversible bond in the material that can be broken and reformed on demand. And this kind of bonds give the self-healing functionality. If we check what are the kind of bonds or the kind of interaction that we can have in this kind of polymer, there are reversible covalent bonds, so bonds that share electrons, like for example sulfur-sulfur bonds or disulfur bonds. We have a chain entanglement, so polymers are formed by chains, and when you make a crack on a material, chain gain mobility at interface, repairing the damage. We have also non-covalent bonds or non-covalent interaction, like for example hydrogen bonding or ionic clustering. And also in this case, these kind of bonds are reversible and can be reformed in a damaged site. The mechanism for all this self-healing material, this self-healing polymer, is always the same: to gain mobility in the material. And the gain mobility is associated to a decrement in viscosity. So, when a damage arrives in the material, the chain of the polymer gain mobility, reconnect together at the damaged site, and this mechanism can be repeated several times. The trigger can be different, can be a change in stress, a change in temperature, but also a change in pH or UV, depending on the self-healing system that you want to design. Now we want to insert this material in a spacesuit. So there are different strategies. We have, following a self-healing approach, an environmental reaction or chemical reaction. In the first case, one material, reacting material, is embedded inside the stacking sequence of the spacesuit. When a damage arrives, this material flow in the damaged side, react with the environment, can be a reaction with the oxygen, that creates a foam and seals the damage. Similar to this one, there is a chemical reaction where two fluids that can react together flow in the region of the damage, sealing the damage. We have also other two approaches, mechanical coverage, where an elastomer pre-compressed is inserted inside the material. When the damage arrives, the material relaxes, enclosing the hole. And then we have a flowing material approach, where a material, during the damage, activate all the mechanisms for healing, flow inside the damage, sealing it. And this one is the one that we select for our research. So we select this class or this strategy for the self-healing for our spacesuit application. The first material that we select for this application, or we tested for this application, is an ionomer. It's a polymer composed by two parts. It's a copolymer formed by ethylene and methacrylic acid, and the acid part is neutralized by ions. In this case, in this particular case, is sodium ions, and these bonds are the reversible one inside the polymeric material. What we want to check is the capability of this material to repair after a projectile that passed through it. So the projectile passed to the material itself is able to close and seal the hole. This material has a very nice property. It's a self-heating behavior. When you stretch this material at moderate or high velocity, it gains in temperature. So in this particular case, we stretched the material around 1 meter per second, and there were an increment of about 30 degrees. And this can give us enough mobility, so when increasing temperature, the material gain in mobility, to have an efficient self-healing behavior. This one is for stretching, so for tensile test. We did the same during the impact. We record with a IR camera the impact site, and we saw that the material effectively have a phase change during the impact. So we pass from room temperature to up to 120 degrees, more or less, and this increment in temperature gives enough mobility to repair the damage, and the ionic bond recover the original network of the material. This one is the sketch of the test. Here how it works. A projectile arrives, there is the change of phase of a material when the material passes through it. The viscous behavior of the material allow the mobility, but the liquid, the polymeric liquid, still have enough elastic properties, rebound back, seal the hole, and during cooling there is another phase change from liquid to solid. In this case is a good example of how the self-healing material works. The question is, there is a limit on this kind of self-healing behavior. We design a huge experimental campaign playing with the velocity of the impact, the shape of the bullet, and the thickness of the sample in order to check the capability of self-healing for different applications. In particular, for spacesuit, we tested at hyper velocity up to 4 km per second, so very high impact velocity. And we designed a depressurized airflow test to check the efficient sealing of the sample, and we observe the surfaces of the sample with a microscope. So just to give you some result, here the test at low velocity, up to 180 meters per second. We detect that there is a critical ratio between the bullet diameter and the sample thickness for healing. In particular, for this velocity, this ratio is 0.2. So below this ratio, there is no healing. Above this healing, and effectively for the healed sample, there is a melted zone in the central part. So melting is important to gain the mobility to repair the component. We move then to hypervelocity, so from 2 up to 4 km per second. And also in this case, there is a critical ratio for healing, but there is a different conformation of the damaged site, but still a large number of samples show the self-healing behavior and sealing capability. This is the picture of our polymer. If you compare this kind of damage on different material, example, the same test performed on aluminum alloy, here the damage is of about 5 millimeters with no healing at all. So this is our self-healing polymer and a sheet of aluminum with the same thickness tested at the same impact velocity. The same can happen in space. Here you can see a damage on a solar panel, so with more or less the same dimension of debris and no healing at all. So you see how the material is well performing after the bullet passage. Then we create this kind of chart, putting together the velocity and the critical ratio for healing with the two regions for healing and no healing. We take our material and we create a stacking sequence, mimic the space suit configuration. We have our fabric, the external part, we have the self-healing layer, and we have the bladder. We may re-perform the test, and also in this case, there was a good self-healing properties. So the material is able to seal and repair this kind of damage. The problem that pushed us to make more research in this direction is that the healing behavior do not appear below a critical velocity. Below 150 meters per second, there is no healing at all. So what we did, we start a collaboration with a chemical company, Solvay, to develop a material suited for this application. So a material that is have all the characteristics that we need for our spacesuit. So we start from already an elastomer certified for a space application. We modify chemically the material, putting inside the dynamics bond and playing with the polymer architecture. This allows us to control the viscoelasticity of the material, so the capability of flow of the material and the self-healing properties and the healing properties. We also design a new test apparatus to test the damage in quasi-static condition. Here there is a pressure vessel where we put our sample, a probe that is moving, perforating our sample, and we check the airflow inside the sample to check in how much time the material is able to seal this kind of damage. Here the sketch, and here our testing device. What we want to check, or our target, were to minimize the peak flow during the impact site in order to avoid the problem of explosion, to minimize the loss volume, so we want to lose a minimum amount of fluid during the healing event, and we also want to have a minimum flow after the repair. This flow should be 0 to seal completely the spacesuit. Then we create different polymer, we create our sample with still the fabric, the self-filling elastomer, and the bladder. We perform our test, we insert the material in our testing system. Here's this probe that is moving, perforating the sample, and here the result. In blue, you can see here the reference sample, so without any healing rubber inside. Here the polymer that we develop in collaboration with Solvay. And you can see that all these polymers perform well, so have a good response, a good self-healing response. They are able to close the damage, and in particular, the polymer number C is the one that performs better, that have a good low value during the damage, the minimum in the loss volume, so we do not lose any, not so much fluid during the damage and the repair, so in this time, and it's also able to seal complete the damage. So the flow is 0 in this case. So there is no any flow through the material. And this one is the polymer that we choose to further develop our material. So it's the good starting point for a real application in the space field. So to conclude, so we demonstrate that self-healing capability is possible from hypervelocity to quasi-static condition, so impact damage. We demonstrate also that these materials are ready for space application, and they can be easily implemented in spacesuit design, the current spacesuit design. We also demonstrate how the collaboration between different disciplines, from space engineering up to chemistry, is necessary to get to the target, to arrive to the target. But of course, the work is not finished. We are still working on the modeling, so we want to model this kind of self-healing behavior. We are trying to optimize the stacking sequence of the spacesuit, and also we are aiming for environmental testing to send a piece of our material in the space to check the healing capability during a real operation. So with all the treats that we have in space there, and to check if the material is able to work in this condition. So to finish, I want to acknowledge my research group, Laura and Stefano, the colleagues from chemical department that help us on the synthesis of the material, and Solvay for the financial support. And of course, you for your kind attention. Thanks.